Hello, today we will be solving this problem called 2 sets 2. So our task is to count the number of ways numbers 1 through n can be divided into two sets of equal sum. For example, if n is equal to 7, there are 4 solutions. So the only input is the number n and it can be up to 500, and the answer should be outputted modulo 1,000,007 because it will be very large. So let's head to the drawing board and see how we can solve this problem. So as we said, we need to divide numbers from 1 to n into two sets, S1 and S2, such that the sum of all elements in S1 is equal to the sum of all elements in S2. So first, let's try to figure out what this sum is be equal to. So we know that the sum of all elements from 1 to n is equal to n times n plus 1 divided by 2. And we also know that this is equal to the sum of elements in S1 plus the sum of elements in S2. And since these two are equal, I will name them x, and this sum will be equal to 2 times x. Therefore, x is equal to this divided by 2, so it would be equal to n times n plus 1 divided by 4. So just from this equation, we can notice that a solution will not always exist because this product needs to be divisible by 4, which is not always the case. For example, if n is equal to 5, then this sum will be equal to 5 times 6 divided by 4. This is equal to 30 over 4. And this does not belong to the natural numbers. So for the case where n is equal to 5, no solution exists. But for n equals 7, for example, we get 7 times 8 divided by 4. And this is equal to 14. So in the case of 7, it is clear that a solution may exist. Now let's try to find out how we can count these solutions. So let's take the example of 7 and let's try to generate all possible sets that we can create. So basically, let's consider all possible partitioning of these numbers into sets S1 and S2. And it is important to notice here that it is sufficient to consider all possibilities for set S1, because once we know the elements in set S1, we can easily deduce the elements in set S2. For example, if I tell you that set S1 contains 1 and 3, then it is easy to deduce that set S2 will contain 2, 4, 5, 6, and 7. So how can we generate all possible assignments for set S1? We can do that by looping over all these numbers and decide the following. Either we take this number and add it to our sets. I say sets here because we will have many possible sets that we may create, or not add it to the set. This will become clearer once I work out this example. So at the very beginning, at step 0, I haven't chosen any of these numbers yet, so I only have the empty set. Okay? Now in the next step, in step 1, I will decide what I will do with this one. So I can either take it, and if I take it, I will add it to this set, or I choose not to take it. Then the sets I had before will remain unchanged. So if I take one and I have to add it to the empty set, so I will have a set containing 1, And if I don't take it, I will be left with what I had before, which was simply the empty set. Now we move on to the second element. So in step 2, I can choose to take this 2, and if I take it, I can add it to any of the previous sets I had. So if I add it to this first set, I will have a set with 1 and 2. And if I add it to this second set, I will have a singleton with only 2. And I can also choose not to add it. And in that case, I will be left with the sets I had before. So I will be left with 1 and the empty set. I will do the same thing with the third element. So in step 3, I can either choose 3, and if I choose it, I have to add it to all these sets I had before. So I will get the following. Or I can choose not to choose it, and in that case, I will have all the sets that I had before. So I will get the following. Now you may notice that the number of sets we have to consider doubles after each step. So we started with 1, and then we had 2, 4, 8, and in the next step we will have 16. So it is clear that generating all possible sets and then seeing which ones satisfy our condition will be too expensive, because we will need to generate 2 to the n sets, which is huge. So instead of doing that, let's remind ourselves what we are looking for. So as we said, we need to find all assignments to set S1 such that the sum of S1 is equal to the sum of S2. And in this case, it will be equal to 7 times 8 divided by 4, as we said, which is equal to 14. So we want the sum of our set S1 to be equal to 14. This actually is important because it will guide us in choosing whether to add an element to S1 or not to add it. So if we continue here, when we come to step 4, we can choose to take this value 4, and if we do so, in this first set, we will have the following. And we will have other sets that I do not care about. But look what happens now when we get to value 5. So for value 5, we can either take it or not take it. So if we take it, we have to add it to this set. But what is the sum of elements in this set? It is already 10. So if we add 5 to it, we'll go above our target of 14, because the sum of this set with 5 will be equal to 15. So it does not make sense to choose to add 5 to this set, because generating this set and all the subsequent sets that may emerge from it will not fulfill our condition and therefore should not be counted. But the decision we just made sheds the light on what matters most to us. If you see here, we laid the actual values in each set, but that's not what we cared about when we decided whether to add 4 to this set or not, because here we only cared about the sum. So this tells us that instead of keeping the values as they are here, we should only keep the sums they represent. And if we do so, all possible sums that we may encounter are, as we saw, limited between 0 and the maximum sum that will happen if we take all elements, which is n times n plus 1 over 2. And the maximum value for n is 500, so this will be like 500 times 501 over 2, which is of order 10 to the 5. And these values are way smaller than 2 to the n we had to begin with. So instead of keeping the sets in the explicit format like this, we shall only keep the size or the sum of elements of each set and the number of occurrences of each size. So this shall represent the size of each or the sum of elements of each set, and here I will note the number of occurrences. So in the first step, we only had one set of sum 0, so I will put a 1 here. In here, I had two sets, one with sum 1 and another one with sum 0, so I'll put a 1 here and a 1 here. For the third set, I had 4 sets with sums going from 0 to 3. So I'll put a 1 here, a 1 here. In the third step, I have 2 sets that add up to the same value. So I will have 1 here, 1 here, but for 3, I have 2 sets that add up to 3. So I'll put 2 here. Then I have 4, 5, and 6 as well. So now let's see what we get for value 4. For 4, we have two choices. As we said, we can either take it or not take it. So if we take it, all these values will contribute the same amount to the actual value plus 4. So here for a set of sum 0, it will also contribute to a set of sum 4. So here we can do one of two things. We can either start from here or from the other direction. So notice what happens if we start from here. So first of all, we will get these values for free because they represent the case where we choose not to take 4. So we will get 1, 1, 1, 2, 1, 1, and 1. So as we said, we're gonna go in this direction, and for each value, we will increment that same value plus 4. So here, we should increment the value for 4, which is this one, by 1, so this becomes 2. We should also increment the value for 5 with 1, so this becomes 2 as well. And we will do the same thing for 2, so 6 becomes 2 as well. Now for 7, we should increment its value by 2, so this becomes 2. The same thing for 8, because 4 plus 4 is 8, so for 8 we will have 2, and the same thing will happen for 5. So 5 plus 4 is 9, so the value for 9 will become 2, and finally for 6, if we add 4 to it, it will become 10, so the value for 10 will be added to as well. But you can clearly see that this is wrong, because the value we had for 4 was just 1, but we actually, by going in this direction, we overwrote the value for 4 before we could propagate it. Now let's see what happens if we go in the other direction. So as we said, we're gonna get all the other values for free, so we get 1, 1, 1, 2, 1, 1, 1, and then we start from the end. So 6 plus 4 is 10, so we will have 1 here instead of 2, so this was wrong. The same thing here for 5 plus 4 is 9, so we get 1 here instead of 2. For 4 as well, so we get 1 for 8 instead of 2. For 7, so 3 plus 4 is 7, so we actually get a 2 here, and now we keep on going. So 2 plus 4 is 6, so we update this to 2 because we will add this one to it. The same thing will happen for 1. 1 plus 4 is 5, so this becomes 2, and 0 as well, so this becomes 2. And this is the actual result that we get. So basically, we can just have an array that goes from 0 to our target sum, and each time we loop through that array from the end to the beginning in order to avoid overwriting values that we will later propagate. We could avoid this headache by using two arrays, but it is more tedious than this. we should rather just use one array and go from the end to the beginning. That way, any value that is propagated will never be propagated again. So we can make sure that the value stored in it is the actual value. So now if I ask you what is the answer to this problem, you would tell me that we will only have to generate this array taking into account adding values modulo the prime given, and if we call this array dp, then the answer will be dp of n times n plus 1 divided by 4. But this is not entirely true. If you look at this example for 3, so if n was equal to 3, then this array will be the whole thing that we generated. And 3 has a solution because 3 times 4 divided by 4 is equal to 3. So there should actually be a solution that sum up to 3. And here, what do we get? We get that the count for 3 is 2. So we have these two. So we can pick S1 to be 3, and then S2 will automatically be 1, 2. And we can also pick S1 to be 1, 2, then S2 will be 3. So what we did here is that we double counted the answers. Both these answers should be accounted for only once. So basically, we need to divide this by 2 in order to avoid counting the assignments for S1 and S2 independently. So the answer we obtain here should be divided by 2. However, this is problematic because this value we calculated was calculated modulo our prime p. And when we are doing modular arithmetic, a over b modulo p is totally different from a modulo p divided by b modulo p. So in this case, we cannot just calculate this modulo p and then divide it by 2 modulo p. So what we actually need to do is to find the modular inverse of this b. So basically the modular inverse, I will note b minus 1 in this case, is such a number that when multiplied by our number b here will give us a result of 1 mod b. So without being too rigorous, we can do the following here. We can multiply by b inverse the numerator and the denominator here modulo p, and what we obtain is that a times b inverse divided by 1 is congruent to p. And in this case, we transform the division we had into a multiplication, which is good. So here when I say b inverse, it's not actually a fraction, but it is also a number from 0 to p minus 1. So for example, in this case, the modular inverse for 2 would be 500 million and 4. Why? Because if we multiply 500 million and 4 by 2, so namely b times b inverse, we will get the product of 2 times 5 to the 8 plus 4. This will give us what? It will give us 10 times 10 to the 8 plus 8, which is equal to 10 to the 9 plus 8. And this is congruent to 1 modulo 10 to the 9 plus 7. So as you can see, this number is the modular inverse of 2 because when we multiply them, we just get 1 modulo our prime. So in this case, instead of dividing by 2, we can just multiply a by this huge number. Now you may ask, how did I come up with this number? Well, this number is actually equal to 2 raised to the p minus 2. Where p is my prime 10 to the 9 plus 7. So basically the modular inverse of any number with respect to some prime would be just that number raised to the p minus 2. If you want to learn more about this, I invite you to watch the video I will put in the description box. So that's pretty much it. We just need to generate this array dp as we saw. We will make sure that we go backward to avoid double counting, and we will first check that a solution exists by checking that this sum is actually divisible by 4. And at the end, we will overcome the problem of dividing by 2 by actually multiplying the answer we got by the modular inverse of 2, which is this number. So finally, this is our solution. I start by storing the modulo into this variable mode. Then I use this function here, which is the modular binary exponentiation that we saw in another problem, in order to compute the modular inverse of 2. And for our program, we will start by inputting n. Then I will calculate the total sum. And in order for this problem to have a solution, this sum modulo 2 should be equal to 0. So if the total sum is odd, there are no solutions and we stop there. Then I calculate my target sum, i.e. the sum of each set, and it is going to be equal to the total sum divided by 2. Then I declare a vector that will store the count of each sum, and here I only need to go from 0 to the total set sum. So that's why I go from 0 to set sum plus 1. Make sure to add this one here because we actually are going to need that extra cell. Here I start by setting the sum count for 0 to 1. This accounts for the empty set we start with. Then we will loop over all values from 1 to n included, and for each value we will loop from the largest target sum to the actual value in decreasing order. Because as we said here, we will go in this direction, starting from the end and going in the reverse direction. For example, if the value I am actually computing is 4, then I will start with 14 and I will go 14 minus 4 is 10. So whatever value was stored in 10 will be updated to 14. And that makes sense because if I had some value here at 10 and I choose to take 4, then I will reach 14. And we said we need to do this to avoid overwriting values in the process. And here I will stop at the actual value itself because once I reach 3, I cannot go 4 steps in this direction. So here at each iteration, I have to update the sum count by the sum count at position sum minus value, and all this under the modulo. And at the end, I just output the value I got at set sum after I multiply it by the modular inverse of 2. So that's pretty much it. Let's go ahead and submit. So that worked. Thank you for watching. See you in the next video. Bye bye.